Machine learning can so often feel entirely dominated by these hyper-complex neural networks and hidden layers. But today, we're actually looking at the architecture of logic itself. Welcome to this explainer. We are diving deep into the decision tree. It's an algorithm that's just so incredibly intuitive because it quite literally mimics how you and I make choices every single day. Okay, let's take a quick look at our roadmap. We'll start with the logic of decision trees, move into the anatomy of the algorithm, break down exactly how it works, look at its strengths and fixes, and finally explore its real-world uses. All right, diving right into Section 1, the logic of decision trees. To truly grasp this concept, we really don't need to start with lines of code. Just think about your morning routine. You look outside. Is it raining? Well, if the answer is yes, you grab an umbrella. If the answer is no, you just keep walking. Without even realizing it, you are running a rudimentary decision tree algorithm right there in your head. You evaluate a specific condition, and based on a super simple yes or no outcome, you take a distinct path. Machine learning decision trees do the exact same thing, just at a massive, massive scale. Let's escalate that analogy to a real-world business scenario for a second. Imagine a bank evaluating a loan application. The algorithm might start by asking, is the customer's monthly income greater than $3,000? If no, the loan might just be immediately rejected. If yes, boom, it triggers the next question. Does the customer have a good credit score? And this just cascades down until a final decision is reached. It perfectly shows how a basic yes or no questioning framework can scale up to handle incredibly complex financial evaluations and make highly accurate business predictions. Moving on to Section 2, Anatomy of the Algorithm. So why exactly do we call this thing a tree? Well, when it's mapped out, it looks exactly like a tree, just upside down. At the very top, we have the absolute beginning of our data split. We call this the root node. It represents the first and honestly, arguably, the single most important decision the algorithm makes to begin separating the data. And remember, there is only ever one root node. The really crucial part is how the rest of the structure flows down from that root. As we move down, we hit what are called decision nodes. You can think of these as the follow-up questions or conditions, like that "is their credit score good" question we mentioned earlier. Connecting all these nodes together are the branches, which are simply the outcomes of those decisions, the actual yes or no pathways. Finally, at the very bottom, where all the branching completely stops, we find the leaf nodes. A leaf node is your final prediction or decision, something like approve loan or reject loan. Let's get into Section 3, how the algorithm works. Now that we've got a solid mental map of the anatomy, let's look at how these pieces actually move together mechanically. It happens in 5 distinct steps. First, the algorithm collects labeled training data, say, historical records of exactly who did and didn't pay back their loans. Second, it evaluates all the available variables to choose the best feature to split the data on. Third, it actually executes that split based on the feature, which creates more uniform similar subgroups. Fourth, it just repeats this process, picking the next best features and splitting again and again until it finally hits a logical stopping point. And then step 5, the tree is fully ready to make predictions on entirely new, unseen data by routing it from the root all the way down to a leaf. But you might be wondering, how does the algorithm mathematically decide what the best feature to split on actually is? Basically, it measures the messiness. One of the primary tools it uses for this is called Gini impurity. It's a mathematical measure of just how mixed up the data is after a split. The algorithm is constantly hunting for the lowest possible Gini impurity score, because a lower score means the resulting groups are cleaner, they're better separated, and they're a lot less mixed. Now, alternatively, the algorithm might use concepts known as entropy and information gain. You can think of entropy as a measure of the chaos or the uncertainty in the data. Obviously, the algorithm's goal is to reduce that chaos. Information gain measures exactly how much that uncertainty drops after making a specific split. So the algorithm effectively hunts for the purest possible groups by always choosing to split on the feature that provides the absolute highest information gain. And honestly, this brilliantly illustrates just how insanely versatile this algorithm is. Depending on what you're actually trying to predict, the tree completely adapts. If you're predicting a category, like figuring out if an email is spam or not spam, or if a patient is healthy or has a disease, you'd use a classification decision tree. But if you're predicting a continuous number, like forecasting next quarter's exact sales revenue or predicting the price of a house, you use a regression decision tree. It's the exact same intuitive logic, just delivering completely different mathematical outputs. All right, jumping into Section 4, strengths, weaknesses, and fixes.
let's evaluate how this algorithm actually performs out in the wild. The decision tree has some truly massive strengths. First and foremost, it is just incredibly easy to understand and graphically visualize. You could literally print out the tree on a piece of paper and explain the model's logic to a CEO or a stakeholder without needing to explain any complex math whatsoever. It seamlessly handles both numerical data and categorical data at the exact same time, plus it requires very minimal data preparation. In fact, you often don't even need to normalize or scale your data before feeding it into the algorithm. But hey, every superhero has its kryptonite, right? For the decision tree, the absolute biggest danger is overfitting. Overfitting happens when the tree is allowed to grow way too deep and become way too complex. Instead of learning the broad general patterns in the data, it essentially just memorizes the training data perfectly. When this happens, it's going to perform terribly on new, real-world data. It's also highly sensitive. Literally, a tiny, minor change in your dataset can result in a completely different tree being generated. Fortunately, though, data scientists have some pretty solid cures for this. The most common fix is called tree pruning, which is exactly what it sounds like. You're literally chopping off unnecessary, highly specific branches that just don't add broad predictive value. You can also proactively limit the maximum depth the tree is even allowed to grow in the first place, or you can set a hard rule that a node must have a minimum number of samples before it's ever allowed to split. These techniques constrain the tree, which completely prevents that overfitting issue and vastly improves its ability to generalize to new data. Let's bring it all home with Section 5, Real-World Applications and Evolution. Stepping completely out of the theory for a second, the broad, real-world utility of decision trees becomes pretty undeniable. Over in healthcare, it's literally saving lives through rapid disease diagnosis. In banking, it's instantly approving loans and immediately throwing up red flags for fraud detection. Marketing teams are using it to segment their customers and predict who is most likely to cancel a subscription. Even in manufacturing, these trees are quietly working in the background, constantly analyzing quality control metrics and predicting equipment failures long before a factory line actually breaks down. Let's ground this in a really specific high-stakes hospital scenario. Imagine a doctor needs to assess a patient's risk for heart disease. A decision tree takes that patient's data and cascades through some layered questions. Is their age over 50? Then, do they have high blood pressure? Then, is their cholesterol high? And finally, are they a smoker? Each one of these questions refines the risk profile, which allows doctors to use this completely transparent model to actually support critical clinical decision-making. So how does it actually stack up against other models? Well, compared to a classic linear regression model, the decision tree very often has the upper hand when things get a bit complicated. See, linear regression assumes a straight line, linear relationship between variables. And let's be real life rarely follows a straight line. Decision trees, on the other hand, are just fantastic at learning complex, nonlinear relationships, all while remaining incredibly easy to visualize. However, when we compare a single decision tree to an algorithm called random forest, we really see the next step in machine learning evolution. A single tree is super fast, but as we discussed, it's prone to that overfitting issue. A random forest solves this entirely by generating hundreds or even thousands of different decision trees and having them essentially vote on the final outcome. It's an ensemble method. The single tree is just the fundamental building block that makes the highly accurate, incredibly robust random forest possible. And honestly, that brings us to a massive, vital takeaway. Mastering the simple logic of a single decision tree, that is your foundation. Because once you understand exactly how one tree splits data and reduces uncertainty, you possess the conceptual key to understanding absolute artificial intelligence powerhouses like random forest, XGBoost, and gradient boosting. Which leaves us with this final thought. We've seen exactly how this algorithm elegantly bridges the gap between everyday human logic and highly advanced machine predictions. The architecture is sitting right there, ready to be utilized. So, how will you use the intuitive logic of decision trees to unlock complex patterns in your own data? Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.